Let's talk about energy diagrams. So what is it? It basically is just something that tells the story of what's going on with regards to energy during a chemical reaction. There's only two types of shapes. Okay, there's one that goes up and down a little bit, and there's one that goes up and way down. So which one do you think is exothermic? Well, exothermic reactions release a lot of energy. So I think B, because if you go up and then way down, you're releasing a lot of energy because the products don't need as much energy as the reactants. So B would be the exothermic, and then A would be the endothermic, where overall the products absorb energy from where they were at. So here's what it says. Because an exothermic reaction releases energy, the products would have a lower potential energy than the reactants. So you should have circled B. In the endothermic reaction, energy is absorbed overall, and so the products would have a higher potential energy than the reactants. So you should have circled A. The triangle H shown in the diagrams is called the heat of reaction. Okay, you can see it right here. Okay, it's the difference in energy between the reactants and products. It is negative in an exothermic reaction, symbolizing a release of energy. They could have labeled it negative here. And in an endothermic reaction, it is positive, symbolizing that overall it's absorbing energy. Question, in a combustion reaction, would the heat of reaction be positive or negative? Well, combustion is exothermic, so it would be negative, because here it says it would be negative for an exothermic, releasing energy. In the diagrams above, the EA, the activation energy, is the energy required to break the bonds of the reactants. As you can see, both of these diagrams are exothermic. They both go up and way down. But diagram A has a smaller activation energy, and therefore this reaction will be more likely to happen. When your body breaks down food, is energy required or released during the breakdown process? You need energy to break down the food. It's kind of the opposite. We always say, oh, food gives us energy. But actually, it's a little more complicated than that. First, your body needs to break the bonds of the food, which requires energy. Luckily, overall, it releases energy. So you get that energy back. In the diagrams above, the blue highlighted area shows where energy is required to break the bonds of the reactants. The pink highlighted area shows the intermediate stage, where atoms are single and ready to mingle. And the yellow highlighted area shows where energy is released as new bonds of the products form. Question, in an endothermic reaction, the energy released when new bonds form is greater than or less than the energy required to break the reactant bonds. Well, let's look. Here's an endothermic reaction. There's all the energy required to break the bonds, and then here's all the energy being released back. So that is less. The energy released is less than the energy required to break the bonds. And that's why it has that shape of overall absorbing energy. Let's look at some examples of energy diagrams with real chemical equations. So here we've got methane, CH4, reacting with two oxygen molecules, and their bonds break. Look, they're all single. This is the singles party. Single, woo! And then they rearrange and they form new things. So they form CO2 and H2O. And then it has the energy associated. So, okay, it took 634 kilocalories per mole. It released 828 kilocalories per mole. So overall, if you account for the energy you had to put in, it's releasing 194 kilocalories per mole. So in the above reaction, methane gas reacts with oxygen gas to produce carbon dioxide and water. What type of reaction is this? This is a combustion. Classic. How much energy per mole is required to break the bonds of the reactants? 634 kilocalories per mole. How much energy per mole is released when the bonds of the products form? 828 kilocalories per mole. What is the value for the heat of reaction? Negative 194 kilocalories per mole. Is this reaction exo or endothermic? It's exo. More energy is released than energy required to break the bonds. And then let's take a look at an endothermic reaction. For the reaction above, the activation energy is 1443 kilojoules per mole. It's a different unit of energy. The energy released when the bonds of the products are made is 1,214 kilojoules per mole. Okay. Highlight the activation energy, the energy to break the bonds in blue. The transition state, pink. And the energy released in yellow. Obviously not drawn to scale. Calculate the heat of reaction. So 1443 minus 1214. Punching this into my calculator. 1443 minus 1214. That's 229 kilojoules per mole. So that would be the heat of reaction. The overall energy absorbed. And this would also be a combination reaction. Two things adding together to form one product. All right, there you go. A little introduction to energy diagrams.